Thank you. All right, thanks everyone. This is 13 ways of looking at a turtle, and I'm Scott Wlaschin. Um, this is a bit of a crazy talk, actually. Um, Rather than doing a deep dive into one topic, I'm going to do 13 very, very shallow dives in using the same model, which is turtles. So this is, we're going to do partial application. Most of these techniques will be sort of functional techniques. So we'll talk about partial application, functional error handling, state monad, actor model, event sourcing, dependency injection, interpreter, capability-based design. So 13 different turtle designs that we're going to look at. And I'm already out of time because we have an hour to do this, and it's about 4 minutes per topic. So that's this is how I feel right now. It's crazy. If you like these kind of crazy talks where I do a lot of things in 1 hour, I have another talk on functional programming patterns, also very fast and crazy. So I'm going to be using F# for the code examples, but this is actually a concept talk, and these concepts will work in pretty much any programming language. So if you're not familiar with turtle graphics, you have a turtle and it moves, and then it changes direction, and it moves, and then it changes direction, and it moves. So that is it, and there's a pen which draws lines, and the pen can be up or down. So it's a really, really simple model. How many different ways, how complicated can we make this very simple model? We're going to make it really complicated because that's what we like to do. So here's our API. There's 4 different operations: moving a distance, turning an angle, putting the pen up, and putting the pen down. So that's our 4 operations which we will implement in many, many, many different ways. So let's start with the object-oriented turtle, the OO turtle, which is also called a tootle. So this is how a turtle works in an OO style. We have some sort of client that wants to run the turtle, to talk to the turtle, and we have a turtle class. And the turtle class is encapsulated. And so the client does not know anything about the internal state of the class. So that this is classic OO, encapsulated mutable state. So the client calls the turtle, says, or it actually sends it a message in true OO. Send a message, here you go, can you please move here? Can you please move here? And I don't get any response back. I just say, okay, it just did it. And the internal state of the turtle is not accessible to me. So let's look at the code. This is the F# version of object-oriented code. I have a turtle class, and there are 3 different fields in the class. And in F#, mutability is something you have to ask for. Everything is immutable by default. So you have to use a special or mutable keyword if we want to modify the fields. And the other thing I should point out is I'm using a nice F# feature called units of measure. So I'm saying here that the angle is measured in degrees rather than radians. So this is a nice documentation thing, and it's also a nice type-safe thing. So I can't mix up degrees and radians accidentally in my code. Right, so let's look at a method. Here's the move method in F# style. I'm going to just log that I moved. I'm going to keep track of the current position. I'm going to calculate a new position using some logic that I don't care about. And then I'm going to draw a line. If the pen is down, I will draw a line on the canvas. And then I will update the state. I will update the current position to be the new end position. And we have a dependency on the logger, and we have a dependency on the canvas. So I will talk about later on, I'll talk about how to get rid of those dependencies. But for now, we'll just hard code that there is a canvas and there is a logger. This backward arrow is F#'s version of assignment. It's not using equal, it uses a backwards arrow for assignment because most things we rarely use assignments. So let's look at the turn method. Again, I'm just going to log it. I'm going to calculate the new angle using some sort of formula. And then I'm going to update the angle. Now I'm not actually going to move the turtle. I'm just rotating the turtle to point in a different direction. And to change the pen state, I just update the pen state up and down, depending. So those methods are really, really simple. Right. Now, how do I call this turtle from as a user of this turtle? So let's say I want to draw a triangle. Well, I'd say, okay, create a turtle, construct a turtle, and then ask the turtle to move a certain distance, and then ask the turtle to turn and move and turn and move and turn. And at this point, the turtle should be back home again. and I should have drawn a turtle. I should have drawn a triangle onto the canvas. So let me actually demonstrate that this is a real thing. So I have a OO turtle right here. I'm just going to load it up. And I'm using F# interactive, which is nice. You can kind of interactively play with F# code. So here's my canvas. I'm going to open up a canvas with a little bit of luck. All right, my zoom is a bit slow. Here we go. Right, I'm going to create a turtle. I'm going to move a certain distance, turn an angle, move a distance, maybe move again, move another angle, move, and so on and so forth. So here is the triangle logic that I just showed you. So I can clear the canvas, draw a triangle, and here's the polygon logic. And I can draw a polygon, and I can draw a pentagon, and a hexagon, and so on. So there you go. That's very simple. This logic, it looks very object-oriented. You've probably seen this kind of code millions of times before. But there you go. Object-oriented turtle. Not much to say about it, really. So what are the pros and cons of an object-oriented turtle? Well, the advantage is it's really familiar. Nowadays, everyone understands object-oriented programming, so it's sort of nothing special. The downside is that it's a stateful system, that it mutates state inside, and it's a black box, which is sort of deliberate. I mean, it's meant to encapsulate the state. It's not supposed to expose the state to the outside world. But that does mean it's hard to test, because I can't really directly poke inside the turtle and change its state. I have to ask it to do a bunch of things. If I want to move it to the corner in order to test it, I have to send it a bunch of messages. I can't just say start up in the corner, depending on how well the API is designed. But in general, it's hard to test mutation code that is mutation. And it's hard to compose. It's hard to make two turtles, do stuff at the same time. I'd have to create a special double turtle class and proxy the methods or something. Not so easy. And right now we've got these hard-coded dependencies on the logger and the canvas. And later on, I'll talk about how to do dependency injection in the OO style and then also in a functional style. Right, so that is the object-oriented turtle. I have a little bell, which I'm going to ring to show that I'm in a hurry, like service, please. Next up. Okay, next is abstract data turtle. So abstract data turtle is where the data is separated from the behavior. So we have a data structure, which is very much like the turtle one. Everything is still mutable, but this is private. So the idea is that nobody else can touch this data and get it wrong. The only people who can touch this data is the turtle functions which we provide. So we have a bunch of turtle functions, and these turtle functions are very much like the object-oriented ones, except these are sort of static methods, as it were, and I have to pass the state in as a parameter each time. So when I move, I pass in the state, and the state will get updated. It will be mutated to the new thing. So it's very similar to object-oriented, but it's not. It's abstract data turtle. So this thing of passing in the current state as the first parameter to a function actually has kind of you can see this in languages like Python, where you pass a self parameter in. That's pretty much how a lot of languages did it before object-oriented sort of took off. And Python was not originally an object-oriented language, so it's kind of interesting how that works. Right. To use it, again, if I want to draw a triangle, very similar code. I construct a turtle, and I keep passing the state in to every single function. And at the end, the turtle state, by passing the turtle state around, it keeps track of where the turtle is. Okay. Pros and cons of this? Well, it's very simple. It's even simpler than OO. And compared to OO, you can't do inheritance. So if you think that inheritance is a kind of code smell, this approach forces you to do composition. Downside is it's just like object-oriented programming. It's got this mutable state, which is encapsulated, so you can't really see what's going on inside it. So again, it's a bit harder to test. Next, functional turtle. Right, what about functional turtles? Well, the difference between functional stuff in general is that in functional programming, everything is immutable. So when I call my turtle, the turtle itself does not keep track of its state. And so it won't mutate the state that you give me. It will actually create a new state and give it back to the client. And then the client has to pass that state in. The turtle will change it and give it back again. So the client has to keep track of the state of the turtle. So from a coding point of view, we have a turtle state object, just like we did before, but this time it's public. Because it's immutable, we don't have to worry about people messing with it and corrupting it somehow. We can make it public. They can reach inside and have a look at what's going on. On the behavior side of things, we have these functions, but unlike the abstract data turtle, we pass in a state and we turn a new state. We don't just like mutate the state that you pass in. We have to return a new state, which is the updated state that keeps track of where it is and what the angle is and what the pen is and all that stuff. So this passing state in and out is a very common thing with functional programming. So let's write some code. We get the initial state, we call the move function, and now we get a new state, and now we call it again, and we have a second state and a third state and a fourth state. So this is nice in the sense that everything's very explicit, everything's very transparent. I can examine the state at any point. The downside is it's kind of ugly. So it's kind of annoying to have to write code like this. Can we make this code cleaner? And the answer is yes, we can. So if we think of these turtle functions, they have an input and an output, where each one returns the new turtle state. And then the next function has a turtle state as input, and it returns a turtle state. So if we want to chain these functions together, we can take the output of the first function and feed it into the input of the second function. And in F#, we do that using piping. And the piping we do is, if you're familiar with piping in a Unix command line or console, something like that, it's exactly the same. We take the output of one thing and feed it as the input to the next thing. So if we take that code, we can rewrite it like this. We can say, get the initial input, the initial state, pipe it into the move function, take the output of the move function, pipe it into the turn function, take the output of the turn function, pipe it into the move function, and so on and so forth. So this vertical bar with the angle bracket is F#'s pipe operator. And it's in Unix, it would just be this plain vertical bar, but in F# it's slightly different. And this is a really nice way of doing things. And lots of other languages are using a pipe operator too, because it makes code look much nicer. So that's the functional version. Pros and cons, because it's immutable, it's a lot easier to reason about. I can, if I wanted to start in the corner, I can just create the state in a corner and pass it into the turtle. It's a lot easier to test because I pass in a state and I get a state out, and I can just make sure that it's doing what it's supposed to do. And it's composable. These functions are nice and composable. Downside is the client has to keep track of all the states. So that's a bit of a pain, but things like piping make it a lot easier. And again, even in the functional one, we still have these hard-coded dependencies on the canvas and the logger and so on. But we'll fix that. Next, state monads. So let's say that we're moving our turtle and we hit the wall and we can't go any further. So what we're going to do is we're going to return something. We're going to return the actual amount moved. So our move function is now going to return a pair of things. It's going to return the state, and it's also going to return the actual distance moved. So if we look at our code, okay, here's the initial state, and then we pass that in, and now we get a pair. And then if the distance is less than we thought it should be, okay, we'll try turning, and then we'll get another state, and then we'll try moving again, and that will return another distance, and so on and so forth. And you can get an idea that this is looking really ugly again. So we keep adding things, and every time we add things, the code gets ugly. But we managed to save the day by adding, making the code look nice again. And that's exactly what we're going to do. Now, what we can't do is use piping. And the reason is because we're now not returning one thing, we're returning a pair. So we just can't pipe the state all the way through because we have this distance as well. So that's not going to work. We're going to have to try another trick. So this is yucky, it's horrible, let's fix it. So what we're going to do is we're going to do another functional trick, which is we're going to transform the function into a different shape. So our turtle function now has two inputs, right? We have the turtle state and then the input with the distance to move or the angle to turn or something like that. And the output of the turtle function is now a pair of things. It's the new turtle state and, the actual distance moved or the actual distance turned or whatever it is. So what can we do to make this more tractable, more easy to work with? We're going to use a trick called currying. And what that does is allow you to turn a 2-parameter function into a series of 1-parameter functions. So instead of a 2-parameter function, it's going to be a 1-parameter function that returns another 1-parameter function. And that's what this is. So if we go back to our turtle function, we can actually think of it as you give me one input and I give you back a function. And this thing of a function that returns another function is a really common thing that happens in functional programming. Functions that return functions is just like all everywhere. So now we pass in the distance we want to move, and instead of getting the actual distance, we get this function. And we're not finished yet. So what we're going to do is take this function and we're going to wrap it. We're going to give it a name. We're going to call it state. So you pass me in the input and you get back a state thing. Now, you have to believe me that there's a way. This is now a 1-bit input function with a 1 output. And there's actually a way to compose these functions. You can chain them together, and there's a trick for doing that. Now, you just have to believe me on what that trick is, because I don't have time to explain it. But I actually had a whole talk about it called the monadster. So if you Google monadster, you'll find my talk on the state monad. So given that we can do this, we can actually rewrite this thing in F# to look much nicer using something called a state expression. So a state expression is a block of code where the state is running through behind the scenes and not visible on the surface. So I would write a piece of code like this. I say move 80. Now, the move function has one input, and there's the state thing going on, but that's now hidden. It just returns the distance. And if the distance is less than 80, I can turn. And again, the turn returns this state thing, but that's hidden behind the scenes. And so I can write code that looks very much like the imperative code, even though there's this state object being passed around behind the scenes. So that's very nice. These state expressions are very cool, and we will see more of these very shortly. So this is not special to F#. Haskell, most functional languages have something like this. Haskell has do notation. Scala has something called for comprehensions. It's a way of threading data through. Right, now, so if we compare the OO style, this was the kind of OO imperative style, moving and then checking the distance, then turning, whatever, and the state expression style, the state expression looks very similar to the OO expression, almost identical. The difference is that in the OO version, this move function is working with the hidden mutable state. So it's not transparent. So I can't really see what the inputs and the outputs are. So it's not very testable. Now this function is working with immutable state, and the data is being passed in and passed out. So if I want to test this function in isolation, it's very, very easy to do. It's just that when you put it together in a pile of other functions, it becomes complicated, so we use this state expression. But individually, the functions are much more transparent. Right. Let me see, is there any... I'm just seeing a question on Slack. No. Okay. Right, so what's the advantages and disadvantages of the state expression? Well, it looks imperative, but it's actually got immutability all the way through it. We've got these composable functions. All the functions are still easy to test. The downsides is it's much harder to implement, and in order to use it, you sort of have to understand what's going on. So you have to be pretty experienced functional programmer to understand what's going on. Right, next, error handling. So let's say that rather than telling me the actual distance moved, I'm just going to give you an error. So you're going to pass me in my 2 parameters, and I will say, yes, you successfully moved that distance, or you failed to move that distance, you hit the wall, and I will give you an error message telling you why. So how can we work with these kinds of functions? So every time we see something like this, a success or a failure, in functional programming, we can use a choice type. So in this case, we'll use something called results, and it's either okay or it's an error. It's success or failure. So you can think of this as like an enum, or you can think of it as like 2 different kind of subclasses. Lots of different ways of thinking about it, but basically you have two choices. They're mutually exclusive, right? It's not both of them. It's one or the other one. So I call these choice types. People call them, the real word for these is sum types, and F# calls them discriminated unions. Lots of different words for these things. Very, very useful things. Right, so let's look at the F# code to implement things using a result. So if I want to move, and I can't actually move that distance, I will return an error saying you moved out of bounds. But if it could work, then I'm just going to update the state with the new position that you moved in. So either you won't move at all and you get an error, or you will move and here's the new state. So there's the error choice and the OK choice. So again, I could sort of implement this in OO using subclasses maybe. It's really easy. In functional languages, this is sort of a standard technique. So now let's write the code that uses the results. So I move something and I get a result back. Now, is it success or failure? I don't know. I'm going to have to do pattern matching. So I have to check each possible case. Is it an error? Okay, it failed. Is it successful? Okay, then I'll try moving again. Now I get another result back. Is that a success or a failure? I don't know. I have to pattern match. Either it's an error or it's a success. And I keep going and going like this. And as you can see, it's going to be ugly. Yuckety yuck. Again, every time we do this, we make really, really ugly code. Is there a way to make this code cleaner? Yes, there is. So we'll use the same approach we did with the state. What we're going to do is create a result expression. And in a result expression, on the surface is the happy path, and behind the scenes is the failure. So when we move, if that succeeds, we can do the next thing. And if it fails, it's do not pass go and drop down to the bottom of the block. So again, we try moving, and if that succeeds, the next thing happens, and if it fails, do not pass go straight down to the end. So we can actually write our code as if everything is succeeding all the time. And again, it makes the code much cleaner to write. So result expression, just like a state expression. And the errors handling behind the scenes. And if you're interested in this, I have a whole talk on this, railway-oriented programming, famously on this whole thing of doing error handling using result. Now, you notice that we still have all these ugly states everywhere, but can we get rid of that? Yes, we can. We can combine the result expression and the state expression to have a result state expression. And now we've got the state being run through the back, and we've got the result, the error handling being done to the back, and our kind of the front end code, the superficial code is very clean again. It looks just like the comparable code. So we can combine these different kinds of things, state and result, together in a really nice way. Okay, pros and cons of results. Well, the nice thing about using a result is it's explicit. We're not throwing any exceptions. We're not throwing exceptions say, oh, you must remember to catch this. We're literally returning like an error code, like old school error codes. What's nice is it looks like happy path code, but the errors are being handled very nicely behind the scenes. Downside is, yeah, harder to use, harder to implement, and it's just a whole new way of working. Okay, next is async turtle. So what if the turtle was a real physical turtle and you were talking to it over Wi-Fi or Bluetooth or radio waves or something? It wouldn't respond straight away. So if you were talking to it, you'd have to use an asynchronous call. So our code would look something like this. We ask the turtle to move asynchronously, and we would have to have a callback. We would have to wait for the call. When the turtle finished moving, it would call us back and say, okay, here's my new state. What do you want to do with it? And I say, okay, I want you to move again. And I have to wait for the callback to complete. And then the callback comes back and say, okay, here's my new state. What do you want to do? Okay, I want you to move again, and so on and so forth. And this is very typical of async calls when there's lots and lots of callbacks chained together like this. And it even has a name, which is the Pyramid of Doom, because you get this kind of triangular shape on the sides. And if you have lots and lots of callbacks, it goes very, very deeply nested. These callbacks are very annoying. It would be nice if we could hide these callbacks and not have to be explicit with them, not see them. Is there a way to do that? Yes, there is. Funny you should ask, because we can use another expression. So this yuckety yuck chaining of callbacks is, again, really annoying, and we can hide this using an async expression. So in the async expression, the callbacks are hidden behind in the middle of the expression. So when I say move, that thing on the left-hand side where it says let bang state, that is exactly like C#'s await. So it's like async await in C#, same idea. So we're waiting for the turtle to finish moving, and that gives us the new state, and then we can call the turtle again, and then we await the next state, and then we can call the turtle again. So we basically async await, same thing using the F# equivalent, which is the async expression block. And you might notice that this is good. We've got another async expression. So the callbacks are managed behind the scenes, but the state is still very obvious. How are we going to deal with that? I think you know where we're going. We are going to combine the async expression and the state expression into an async state expression. And now our code looks like this. And again, the everything here, it looks like imperative code, but it's in fact completely asynchronous, and the state is being passed around, immutable state is being passed around, but it doesn't even look like it. So that's really, really nice. Right, what else do we have? Yeah, what is the pattern here? Notice that we're creating all these expressions. We've done this for state, we've done this for results, we've done this for async. The pattern here is the dreaded M word, monads. So all these things are an example of a way of chaining effects together in a nice way and hiding kind of how it works. And monads is the kind of generic name for that pattern in functional programming. And again, I'm not really going to go into it, but you can see there's a lot of commonality between these three ways of doing things. We're basically managing things behind the scenes without making it obvious to the front end of the code here. So the common patterns we've done so far, we've done composition. Everything's been composition, chaining things together. And in the functional code, we have this explicit state management. We don't have any secret mutation going on behind the scenes. We're always passing the state around explicitly, which makes it very, very transparent and very, very easy to test. We've got explicit errors. We don't use exceptions. We use errors which show up in the function signature. And this is a general principle of functional programming, I would say, is we prefer things to be explicit. We don't like hidden things. We don't like magic things. We like everything to be really obvious. And that does make the code look kind of complicated, but then we have these techniques to sort of hide it again. So that's what the M word is. Right, next, batch commands. So let's say that I don't want to manage the state on the caller side because the caller is lazy. How can the caller avoid managing state? Well, one way is to have an intermediary who's going to manage the state for me. So what I'm going to do is going to send a bunch of commands to a batch runner, which is going to run the commands for me. So I now have a new intermediary between me and the turtle. And I'm going to send a bunch of commands to the batch runner, and the batch runner is going to run them, and it's going to talk to the turtle, and it's going to keep track of the state of the turtle, not me. So how am I going to send what are these commands going to look like? What exactly am I going to send to the batch runner? Well, if I was talking to the turtle directly, I would have a bunch of functions I could call. But if I'm talking to a batch process, I can't just call a function. I have to like send stuff down the wire, right? So I need to actually have data structure that I can send. So I need to turn every single function into a corresponding data structure that I can send. Now, how can I do that? Well, I will just create a choice. And for each function I want, I will create a choice which represents that function. So if I, instead of calling the move function, I will say I'll create a choice of the data structure, and in that choice there will be some distance that I want it to move. And I'll have a turn option, and in that turn there will be an angle I want you to move. So there'll be 4 different choices in my data structure, and that is what I'm going to use as a command. So from a usage point of view, I will basically create a whole bunch of commands, and I will send them to the turtle batch runner to run them. So again, this is data. This is not commands. This is a bunch of objects, as it were, and each object represents a function, an action that I want to call later on. So how does the batch runner actually run these commands? Well, it just kind of reverses it. It looks at the the pattern, it pattern matches and says, well, if it's a move command, I'll call the move function. And if it's the turn command, I'll call the turn function. And the pen up function, I'll call the pen, the pen up state, the pen up choice, I'll call the pen up function. Pen down choice, I'll call the pen down function. So it's literally pattern matching. There's a one-to-one correspondence between the choice in the data structure and the function to call. This has actually got a name. This is called defunctionalization, and it's a common technique in functional programming. Now, if I want to run all these commands in a row, what I would do then is basically set up some mutable state. For each command in the list of commands, I would execute that command. That would create me a new state, and then I keep mutating that state, and finally I have the final state after running all those commands. So that's the kind of imperative way where I loop. I just have a for loop. A functional programmer would probably not do that. They'd probably use the fold function, which is exactly the same thing, but just one line of code without any mutable states. So fold or a loop, same thing really inside. But if you are doing functional programming, I do recommend that you learn the collection library. There's a lot of really interesting functions like fold and things that will make your life easier when you're working with collections. Right, next up. Oh no, I haven't finished yet. Decoupled. That is one of the big advantages. I am sending data. I do not know how the turtle actually works because I am just sending you some data for you to interpret. And this idea of interpreting the data is going to be it's very a cool technique, and we'll actually see a bunch of uses of this in the next few examples. It's a lot simpler than monads to keep track of the state this way, so you don't have to learn too much. Downside of this particular one, the batch one, is it's batch oriented, which means that I can't send a single command. There's no control flow. I can't say do a command and then if it fails or something, try something else. It's literally I have a bunch of commands. It's fine for drawing a triangle or a square or something, but it's not good to try and navigate your way around the surface of the canvas. But the control flow thing will be fixed with the interpreter pattern, which we'll be using at the end of the talk. Right, so next, actor model. So the actor model is very much like the batch model, except it's real time. So rather than sending a whole bunch of commands, I will send one single command, which will be interpreted as I send it. So I'm sending a command, I'm putting it on a queue, and the actor is going to pull messages off the queue and process them straight away. It's not going to wait for me to say, okay, here's the last message. So there's a message processing loop in the actor. It pulls a command, it processes it, and it keeps track of the state, again, in the same way that we did before. So let's look at the code for an actor. And an actor basically just has a big loop. It just keeps looping round and round. And the first thing it does is try to read a command from the message queue. And if there's nothing on the message queue, it blocks. So it just stops. But if there is a command, it reads it, and then it updates its states by doing the same thing we did before, matching the command with move and moving the turtle. And then with this new state, it just goes back to the top and recursively loops again. So we don't need to have mutable state. We'll just loop again and wait for another command to come through and just loop and loop and loop. So the actor model is basically a giant loop listening for events on the queue. So the logic inside is basically the same as the batch logic, except it's one at a time. Right, what else do we have? Oh yeah, so as a user of an actor, I'll create an actor and I will send it a message, and I'm going to use the word post because I'm posting it onto a message queue. So I'm going to post the move command, post the turn command, post the move command, post the turn command. And every time I post, it should react pretty much straight away, depending on how the queue is backed up or not. And again, I'm posting data. What I'm putting on the queue is data. I'm not actually passing functions down the queue. So actor model, just like the batch model, it's nice and decoupled. It's also simpler than the state management. Downside is a lot more extra boilerplate to build actors. I mean, a lot of languages have them built in, or there's libraries like Acco and so on that will do it. What else? Yeah, that's it. Okay, event sourcing. I need to hurry because I'm running out of time. I'm only halfway through. Event sourcing. Now, so far in the actor model and the batch model, the state was sort of kept in memory, what happens if we want to persist the state between transactions, right? So I'm going to close this down and start up where I left off. Now, if you have a physical turtle, that's not a problem, but if you have like a logical turtle, that's tricky. So how are we going to persist the state? Well, one thing we can do is just stick it in a database, but let's make it more complicated than that. Let's look at event sourcing. So in the event sourcing model, I have another intermediary, which this time I'm calling a command handler, and I send it a command. And what it does is, rather than loading the current state off the database, it's actually going to rebuild the state by replaying all the previous events. So if I moved and turned and moved and turned, rather than just saying I'm at this position, it will replay the move and the turn and move turn to get back to rebuild the state of what I'm currently doing. So it's just a different way of thinking, but we can store the events in the event store rather than the actual current state. So I recreate the state by replaying the events, and now that the state is sort of in memory, I can go back and do exactly the same logic I did before, which is executing the command, talking to the turtle and doing stuff. Now, after the command is executed, I will want to create an event that represented what happened and write that back to the event store. So if I added another move command, I will now say, okay, I just moved, a few meters or whatever, and I'll put that back in the event store. So now there are 5 events. If there were 4 events before, maybe there's 5 events now. So next time when I replay all the events, I will replay this new one as well, and it will move it. It'll move the logical turtle to where it is. So command versus event, they sound like the same thing, but a command is an imperative, it's an order. I want you to move this distance. I want you to turn this angle. But an event is something that actually happened. I actually moved this distance. I actually turned this angle. I actually changed my pen state. And it doesn't have to match the command one for one. And it's the events are what gets stored in the event storage. So let's look at how you might apply an event, like when you're replaying the events. So it's very similar to the other ones. I basically match what it is. If it's a moved event, I update the state. If it's a turned event, I update the state. If it's a pen changed event, I update the state. Now, all these update the states, they're not actually moving the turtle, right? I am just updating the state in memory. I'm remembering how it would get there to get to the kind of final state of before we start the next bit. So these are not doing anything outside. They're just like updating an internal state in memory. Now, when I want to actually handle the command, the overall thing is load up all the events, replay all the events to get the state before the command happens, and then you execute the command, and that gives you a new event, which you then store back into the event store for the next time. So next time there'll be some extra events that you load up to replay. So when you replay the events in memory, you're not actually doing anything with the turtle. This is very important. You're just kind of updating the logical state. It's only when you do the actual execute command, that's when you actually talk to the turtle and actually move the turtle around. So pros and cons. It's another one which is decoupled because I'm sending data. It's stateless. Again, the state is rebuilt every single time. The system does not store any state in memory that it needs to keep track of. If it crashes, it can reload itself without problems. And it's very nice to support replay of events. In some systems, this is actually very critical. I mean, if you think about financial systems, your bank does not just keep track of your current balance. It keeps track of every single transaction, how much money you put in, how much money you took out, and it replays all that stuff to calculate what your current balance is. It doesn't just keep track of your balance as a number. So in systems where you need that, that's a really, really useful thing to have. Downside is it's more complex, and doing replays of events can be quite tricky. In particular, if you need to version the events, like you have new versions of events and old versions of the events, that can be tricky as well. So pros and cons. I wouldn't reach for it. It's kind of trendy right now, but personally, I probably wouldn't. It wouldn't be my first choice for doing things unless I really, really needed that replay facility. Next, stream processing. Okay, so now we're going to expand our universe and include not just one system, but a whole bunch of other systems, and we're going to call these stream processors. And they are going to have event streams as input and event streams as output. So we have, let's take one of our event processors. and event stream comes in, like things happen in the outside world. And what I'm going to do is I'm going to select them, filter them, transform them. Like most events I probably don't care about, but maybe a couple I do. I'm going to then do the same thing where I turn them into a command. I'm going to run the command handler, and that is going to generate more events, just like we did before. Now, this time, the events are then broadcast to other people. So other people might say, hey, you just moved the turtle. I might be interested in that event because I need to do something, or you just put the pen up or the pen down or whatever. So this is a very good way for doing data analytics. There's quite a few systems where they have these streams of data and you have different processes listening to them. It's very, very decoupled. It's quite nice for certain situations. And of course, the stream process can generate new events, which go down to other systems and so on and so forth. So let's look at a specific example for our turtle. I am going to have a turtle state processor, and what it's going to do is just update the logical state of the turtle. So it's going to keep track of where it is on the board, but it's not actually going to move the turtle. So it's going to generate a series of events like I moved the turtle, I changed the direction of the turtle, all these kinds of things. And I'm going to generate events, and I'm going to have 3 different systems listen to those events. So the first system is the auditing system. It's just going to log everything that happened. The second one is the canvas system. That is going to say, oh, you moved. I'm going to translate that event into a physical movement on the canvas. And the third processor is going to be something that calculates the total distance moved. And maybe I'm going to run out of ink in my turtle. So it's like, after you've moved a certain amount, I need to have a warning that you might run out of ink. So it doesn't care about where you actually are on the canvas. It just says, oh, you've moved how many meters, and it's like time to keep track of all that stuff. So let me actually do a demo of this. Where is my stream pressing demo? Okay. And I will move down here. This is real code. Right, so I'll move down here and highlight this one. So the auditing processor is basically going to handle the various events, and it says if you've moved, I'm just going to log that you moved. And if you turned, I'm going to log that you turned. And if you change your pen state, I'm just going to log that. So that's all it does. It doesn't do anything. It just kind of prints it out. Now, the next one is the canvas processor. And the canvas processor only cares about moves because it doesn't really care about angles. So it's just going to filter out everything other than moved events. And if you did get a move event, it's just going to draw it from the beginning to the end. So there is a subtle bug there, but I'm not going to tell you what it is. Next is the distance traveled processor. And again, all it cares about is moved events. It's going to filter everything else out. And all it does is every time it gets a moved event, it just adds the distance. So it just accumulates the distance over time. And then it prints it out on the screen. So that's all that one does. So we have 3 different processes, all listening. They're all listening to this observable, which is a stream of events. Right, so here's our event stream. We're going to register our 3 processes. And then let's initialize the canvas. Now, so when I move, 3 things happen. So the state gets updated, and that generates an event, a move event. The audit thing is interested in that move event. The distance traveled says, oh, you've traveled 100, and the canvas is interested, and it draws a line. Now, when I do the turn event, the only person who's interested in that is the auditor. The distance traveled person doesn't care. The canvas person doesn't care. If I move again, the auditor cares. The distance traveled is now 200. It's accumulated the distance, and the canvas obviously has drawn the new angle. So that's how the processes work. So if I have a triangle, it's overall I've moved 300. The auditor just went, and the triangle is up to date. So that's how stream processing works. Obviously, in a real system, the stream processing would be a lot more complicated, but it's a great way to decouple the various. It decouples the kind of state management from the physical activities that you take, right? So it's like event sourcing. But sometimes managing the state is one thing, and then physically acting on that or making deductions from that is different. So in this thing is decoupling those two things, separating state management from the actions based on that state. So this is very microservice friendly. A lot of microservices use this kind of approach. Downside is it's more complex. We're going to see how complex can we make a turtle with 4 methods. Like you thought that the object-oriented turtle was complex. No, this is really, really complex. So, but we can make it even worse. We're not finished yet. So in the last few turtles, the batch turtle and the actor turtle, the event sourcing turtle, we've done this conscious decoupling. We're passing data instead of calling functions. And that's, like I say, it's a very useful technique in functional programming. And in the event sourcing one, we're using these immutable data stores. So rather than kind of mutating a database record and updating a database record, we're appending to the event history. We never mutate anything on disk. We just add to it. And that has, from an auditing point of view, that's got a lot of nice properties. Next up, number 10, OO style dependency injection. So here is our turtle class with a move and a turn and a pen up function, and I'm not going to put the pen down method. Now, the move method has 2 dependencies on the canvas and the logger. The turn method has a dependency on the logger, and the pen up has a dependency on the logger. So if I wanted to use a different logger or a different canvas, what I'd probably do is hide them behind an interface. So I'd have an interface which actually has the moves, the logging operations or the canvas draw operations, whatever. So rather than working with a specific canvas and a specific logger, I would create interfaces for these things, and then I would inject those interfaces typically in the constructor with constructor injection. And again, if I wanted to hide the implementation of a turtle, I want a client that draws triangles and squares, I would probably have a turtle interface with the 4 methods being abstract methods rather than concrete methods, right? So I'd have an interface for a turtle, and then I would inject that interface into the client. So that's kind of object-oriented dependency injection, and I'm sure you're all familiar with this. It's very well understood. People have probably been doing it for a long time. Constructor injection is actually required by many frameworks. If you're trying to do something else that's kind of painful, they really like you to do that. Downside is you can easily get unintentional dependencies, because in this case, for example, I'm injecting the canvas, but the only person who cares about the canvas is the move method. The turn method does not care about the canvas, and yet it has access to the canvas. So if I had a bug, I could accidentally change the canvas, or I could accidentally take a dependency on the canvas, which would make it really hard to refactor. The other thing about these interfaces is it's very easy to add more and more methods onto interface, and the interface gets bigger and bigger and bigger. And sometimes I've seen interfaces with 30 or 40 methods on it, because it's like, well, it just exists. I'll just add another one onto it rather than changing all the other stuff. And so they're not very fine grained. Now we have recommendations like interface segregation principle and single responsibility principle and stuff. But these are recommendations, and there's a force in programming which kind of makes us want to add more methods to an object or to an interface. So even though we're not supposed to, it's just easier. And often you need a library to work with it. If you're doing lots of constructor injection, it's nice to just use a library to help you do it. So that's a downside. Okay, next up, functional style dependency injection. So how is that different from OO style? So here we have our turtle module. It's not a class, it's just a bunch of functions. And the move function needs to log information and it needs to draw. And the turn function needs to log, and the pen up function needs to log. Now in a functional dependency, we just pass in the dependencies for that particular function. So the turn function does not need to know how to draw anything, and therefore we do not pass anything in. And the other thing to point out is that we are passing in functions, not interfaces. So I will pass in a draw function. I will not pass in a canvas interface. I will say, this is a function that if you call it, it will draw something, and you do not need to know about the canvas or anything like that. So we're passing in functions, and notice that we only pass in the functions that it actually needs. So there's no accidental dependencies. So how can we passing in all these extra parameters all the time is kind of painful, right? I mean, it's explicit again, but is there a way to make it easier? Well, yes, there is. So let's take these function parameters that we're passing in addition to the main parameter. And what we're going to do is, instead of having a 3-parameter function, we're going to have a 2-parameter function that returns a 1-parameter function. So when we do this kind of thing, what we're doing is we've now sort of, in that 1-parameter function, we've now sort of baked in the parameters that we want. So this is called partial application. You're passing in some of the parameters, but not all of them. So this 1-parameter function looks like this. The log info and the draw functions are sort of baked into it. And from the outside world, it just looks like a normal function. I can just call it by passing in the distance. I don't need to do anything special. So if I actually look at the implementation, here is my move implementation. And again, I now have a whole bunch of parameters, but the dependencies are passed in as functions. So I'm just going to call the log info function. And if I want to draw a line, I call the draw function. And if I want to do, like I say, these are function parameters, they're not interfaces. If I want to do turning, again, I have a logging function that I pass in, and I just call this function with the string that I want to log. And so from a usage point of view, what I do is I probably at the top of my code, I would set up these variant functions or these alternative functions which have the logger and the canvas baked into them, right? So I'm going to bake in these 2 parameters. I'm going to bake in these 2 parameters and using partial application. And what's left is a function with 1 parameter. So now in my main code, I can say move, and I can say turn, and I can say move. And this move function has those things baked in. So the original move function didn't have any baked in dependencies, but I can just bake them in for this particular system, for this particular workflow, I can bake them in. So that's typically how you do things in functional programming, partial application. So pros and cons. The nice thing is that the original functions are completely explicit about what the dependencies are. There's no hidden, like in an object, you can have dependencies on fields that that are not really obvious. We're passing in functions, not interfaces, if we possibly can. And it's a counterforce to having too many dependencies. I mean, if I started passing in 13, 20 different functions for this one function, that would feel ugly. And so there's a natural tendency not to do that. So you kind of get this interface segregation principle for free. It just doesn't feel right to do that. It's fine having an interface with 20 methods. You can just pass it in, it's just 1 parameter. But passing in 20 different dependencies seems really ugly. And so there's a natural tendency not to do that and to refactor your code so you don't do that. And this is a built-in function, a built-in thing of all functional languages. You don't need any kind of special IOC libraries or anything like that. Downside is it's easy to overuse, and I would definitely use it in conjunction with moving I/O to the edges. Like you should be using the onion architecture or the ports and adapters architecture, hexagonal architecture, one of those things where the I/O is all at the edges. So your pure code, in fact, does not need to have any dependencies. It's not actually talking to the outside world. It's not actually, doing stuff. So if you can do that, that's great, because then you don't need to inject dependencies at all. Next, interpreter pattern. Right. So when we design an API, we are actually creating a coupling in terms of exactly what's going on. Let me kind of give you an example. It's harder to talk about. So here's the move function, and I pass in a distance and the current state, and I get back the actual distance moved and the updated state. And if I turn, I pass in the angle and the current state, and I get back the updated state, and so on and so forth. So that's like the kind of original API I would have had for a functional version. And then I say, yeah, but I want to do error handling. I don't want to throw exceptions. So I'm going to put results on top of everything. So now I've completely changed the API. I've broken everybody who uses this API is now their code doesn't compile anymore. And then, okay, so people fix up their code, and then I change my mind again, and I say, actually, I really need these things to be async as well. And now I've broken the API again, and everyone's getting very annoyed with me because I keep changing my mind. Is there a way to write an API that does not break when we change between these different ways of returning results? So I could async versus, is there an API we can write that does not care whether it's async or sync? So, and it turns out, yes, there is. And the answer is to decouple the data. Decouple the API, again, using data rather than functions. And this is, again, defunctionalization. And we're going to do a much more sophisticated one. We saw this with the batch commands and the actor model. We're going to do a much more sophisticated one using the interpreter pattern. So the advantage of this particular one is we can do control flow. We can actually change what we're going to do based on the result from the previous step. So here's how it's going to work. I'm going to send a message, instruction to the interpreter, and that's going to be some data. And the interpreter is going to run it, and then it's going to come back to us with the response. Now, when I send the original instruction, I don't know what the response is going to be. So along with the original instruction, I am also going to send a lambda, which says, when you have finished processing, do this next thing. So it's almost like a callback. I'm going to say, do this thing, and then when you're finished, do this next thing with the result or the response. And then I'm going to send another instruction, and then it's going to interpret it, and then I'm going to pass in a lambda that says, okay, when I get this response, do this. So it's actually not really a back and forth. I'm actually sending the entire program at once. It's actually like writing a little program and having the interpreter interpret the program. So let's look at the code for this. And this is where it kind of gets tricky. So I'm going to call this thing a program. It's a set of instructions. How am I going to model a set of different instructions, a choice between different instructions? Well, I'm going to use a choice type, just like I did before. And I'm going to say, move a certain distance. So the input to the interpreter is the distance. And then the response from the interpreter is the actual distance moved. And at that point, I'm going to say, okay, for this distance, I want you to run this turtle program. So I'm going to pass in a lambda rather than just passing in, a single operation. I'm going to pass in a lambda as well, which is how to respond when the interpreter is finished. And similarly, when I make a turn, I'm going to pass in a lambda as well as the instruction to the interpreter. I'm going to pass in a lambda which says how to respond when the interpreter is finished. And same thing for all the other ones. So it's much more complicated setup. Every single piece of data every single instruction has the input to the interpreter, but also the lambda that's going to be run after the interpreter is finished. So that's the input to the interpreter. That is the response for the interpreter, and then that whole thing. This is the whole thing is the lambda. It's like, given this response, here's the program you need to run. So that's the interpreter pattern as a data structure, right? Again, this is all data, and the interpreter needs an extra instruction. It needs to stop, right? Because it just keeps going on, and it's like, when does the interpreter stop running? Well, I need to say, okay, we're done. We can stop now. So we need a fifth instruction, which is the stop instruction. Right, so that's our, now, so don't worry about understanding this, like I'm literally whizzing through this faster than you can imagine. So let's see how we draw a triangle. So I'm going to ask you to move, and then I'm going to give you this callback or this continuation. When you've moved with this distance, I want you to do this next thing. So I'm giving you a lambda. When you've finished turning, I want you to call this next function. When you have finished moving, I want you to call this next function, and so on. So every single step has a callback or a lambda for you to run the next time you do something, a continuation. So again, we have this code, which is very, very explicit. And then finally, we have this stop at the very bottom, right? That was a new thing. It's ugly. How are we going to fix it? We're going to hide the continuations behind the scenes with a expression, like a computation expression. So we're going to call something an interpreter or a turtle program. And now we can write our code like this. And what's going on behind the scenes is these callbacks, these continuations are being managed behind the scenes for us, just like the async callbacks are managed. So what's nice about the interpreter pattern is you can create a set of instructions and interpret it in many, many different ways. So I can interpret it as moving something on a canvas. I can interpret it as, calculating the distance. The same program can be interpreted in different ways. So here's interpreting it as a turtle. So, when I get the move instruction, I actually move the turtle. And then I loop again and try again. If I get the turn instruction, I actually move the turtle. I actually turn the turtle. So that's the kind of interpreter version of moving the physical turtle. But I could also do something like calculate the distance. So here's the distance interpreter. And again, for moving, all I do is update the distance and start again. And if it's a turn, I don't care. So I don't need to update the distance. And if it's an async, the nice thing about this is the whole logic of how the physical turtle works is completely hidden from me. Whether it's an async turtle or a synchronous turtle, I don't care, because that's inside the interpreter. As a caller, as a creator of the program, I don't care how these things work. I'm literally creating a bunch of instructions to be interpreted. So I think I have a quick thing for interpreter, and then I've got one more, and then I'm sorry I'm running a bit over. Hopefully this is so exciting that you will stay on for a little bit. So there's my instructions that I just showed you on the slides. Here is a program. This is the kind of version with the callbacks, which is kind of ugly. But let's go down to the different ways. So here's my program. I'm going to interpret it as a turtle. And let me start the canvas. So this is a program that draws a triangle, and I'm going to interpret it by drawing things on this canvas. Now, if I take the same program and I interpret it as interpreting by distance, I can then interpret the same program as a distance, and it says you moved 300. So exactly the same program can be interpreted in many different ways. Right, last one. Oh no, not yet. Decoupled, pure API, and optimization. I should just point out you can optimize things. Let's say I move the turtle twice in a row. I can merge that into a single operation. So if I'm doing a lot of things, it's a bit like a compiler optimization. You can compile, if you have 3 instructions in a row, you can merge them into a single instruction. Exactly the same thing for the interpreter pattern. Much more complex, of course, much more complex. So it's best if you have a limited set of operations. If you have hundreds of operations, it's going to be painful. Twitter and Facebook have libraries that do this for their own internal uses. They use exactly the same technique. Finally, capabilities. So what happens often is I make a call and the API says, actually, you can't do that, sorry. I make another call and it says, sorry, Dave, I can't do that. This is really kind of annoying. Rather than, it's very common that you call the API and it says, you can't do that. What about, rather than saying you can't do that, what about telling me what I can do? Rather than let me do something and complaining about it, just tell me what you can do and don't let me do what you won't let me do. So this is a capability-based API, and a capability is kind of like a key. Like if I have a key, I can open this lock. So what happens is I make a call to the API, and it gives me back a bunch of capabilities. And each capability is the capability to do something like move the turtle or turn the turtle, whatever. And if it doesn't give me the capability, I can't do it. So, each time there's a different set of capabilities. Let's say I use the move capability and I get back some more capabilities. So, okay, I can't move anymore. I can only turn, or I can only do something else. I run out of ink. I can't put the pen down anymore. So it's very explicit about what I can do and what I can't do. So, for example, I make a move and I get back the capabilities that I can move and I can turn and I can put the pen down. Okay, so I make another move and I hit the edge, and now I can't move anymore. So the capabilities come back. I only get 2 capabilities coming back. It's like the move capability is not there anymore. So that's, it's very nice. I literally cannot move the turtle because I do not have a way to do that. So the code looks like something. Instead of having a data structure, I have a bunch of functions that I can call from the client. Can I call the move function? Can I call the turn function? In this case, the move function is optional. It may not let me make a move. If that's missing, I won't be able to make a move. So these are all the different keys that I could get to the turtle. And I won't show you the code. So as a user, I would say, do I have the move capability? If I do, I can move. And that gives me some more capabilities. Just now I might have different capabilities than I had at the beginning. So I need to check that again. Can I still move? And if I can't move, then I can't do the second move. But can I turn? Yes, I can turn. But if I can move, I try again. So at each point, I have to check my capabilities and see, can I move them? Can I do this thing or can I not do this thing? So it's a very different way of working, but it is a lot safer. I'm not going to give the demo since I'm running over late. So the advantage of this is the client doesn't need to understand the business logic. Like, have I hit the wall or not? That logic is on the server side. All I need to know is, can I do something or can't I do something? I don't need to understand the rules of the game. And it's much more, from a security point of view, it's much better because I can't accidentally I can't even try to do something that I'm not allowed to do. And you can transform them. Let's say this capability is only available between 9 to 5 on work days, or maybe this capability is only available to this person at this time. You can these are just functions, so you can transform them in lots of different ways. Now the downside is, yes, it's complex to implement, and the client has to change the way it thinks. The client, rather than just having an API that you call, and I'm just going to call the API and see if it fails. The client has to look at all the capabilities that came back and see, can I call them or not? And so the client, the way of coding a client is very, very different. But an example of this is hypermedia as the engine of application state, which is a lot of browser-based capability things. Like if I return a web page that has a bunch of links, if that link's not there, I can't click on it, right? That is websites are exactly this thing, capability-based design. So again, I have a whole talk about this if you're interested, but it's a very interesting approach to doing things. It's very different from most other ways of programming. I recommend you check it out because it's fun. Right, that is it. I'm done. Thank you for staying around. I have slides and videos on my website, and thank you very much.